To start off our series of technical talks for the day, I will give you an introduction to agent communication. So the purpose is to give you a very quick overview of the foundations and common approaches in agent communication languages and agent communication mechanisms, which is a very broad area in itself, so I can only scratch the surface. But just to give you an idea about the kinds of models and views that people use in the agents and multi-agent systems community to talk about communication. Then I'll move on to introduce a particular research challenge I'm interested in within Essence, and that at least one of the fellows projects is about. And then I'll go over a few things that we've done in my group in the past, for the past 15 years almost, toward tackling that challenge. Okay? So, what is agent communication about? So, in the multi-agent systems field, the main concern is obviously with organizing agent activity in such a way that agents can coordinate with each other. So, agent communication basically requires describing two different things. One is the language that agents are going to use for communication, and the other is thinking about interaction protocols. So most interaction does not occur with single kind of atomic messages. Mostly people design interaction protocols that are certain models of dialogues and conversations that serve certain purposes. So that could be, for example, a negotiation dialogue or an auction. So what I want to talk about, to give you some background on this area, is what these communication languages and protocols might look like, and what notions of semantics people commonly use. So because Essence is about evolution of meaning, I want to tell you about what in my area people think of as the meaning of communication among agents. In particular, in the context also of its relevance for coordinating activity, which is the main concern when people talk about agent communication in the multi-agent systems field. And then I'll move on to the challenge bit, which is about decision-making in communication. So that's where I think a lot of interesting problems are. So agent communication languages, by and large, the languages themselves are usually composed of messages, like the example I've given on this slide, where an agent I requests from an agent J to perform an action that involves paying him $500, right? So you typically have these message, obviously you have the sender and the receiver, you have a type of message, for example, a request, which is usually a performative verb from in the sense of speech act theory, which I'll say a little bit about in a minute. And the agents, by and large, exchange these messages. They typically come in a format that's slightly more complicated than in this example, because very often you also need to refer to the content ontology you're using. So, for example, when I say pay me $500, then obviously you need to know what dollars are, you need to know what paying is, and so on. So I need to refer to some usually assumed to be shared ontology. Of course, you can lift that assumption, and then we get into the area of ontology mapping, ontology matching, ontology alignment, and so on. So, as I said before, very often these messages don't come as atomic messages, they come as part of protocols. So, in a very simple request-accept type negotiation, this request message might be followed by an acceptance or a rejection by the other agent. And this already gives you kind of a very fundamental, very simple building block for employing communication in a rational way to achieve some goal from an agent's point of view, or some coordination, some coordinated activity from a more global point of view, because it achieves certain things for the agents. You can also view agent communication languages and interaction protocols as a vehicle for interoperability, because if you think about, if you were just a normal software engineer, not interested in AI or semantics or any of that, one way you can view these languages is to say it's a decentralized system with individual units and components that need to talk to each other, and you essentially agree on a standard for doing that by developing that standard and specifying what the messages are and what they would mean. So in that sense, it also provides interoperability, and especially in the 1990s, a lot of work went into standardization, into specifying standard message formats and languages that can be used for agents. So what is the view that people in this area have on the semantics of these messages and protocols? It mainly is a very pragmatic view of communication. So when I say semantics to the linguists, that might it's almost pragmatics. It's not, it very much focuses on the consequences and the purpose of the communication rather than the actual meaning a message or a statement captures. So a lot of this is based on speech act theory, which goes back to Austin's work and later was further developed by Searle and other people, and which is basically this idea that utterances are produced very much like physical actions to change the state of the world. So if you follow that kind of idea, you don't focus that much on what a particular word might mean, but why I'm like table, but why I'm saying table, right? Or why I'm saying please sit by the table. So why is this popular within the agents field? Well, of course, because we're interested in agents that can perform some intelligent, hopefully, action and that can interact with other agents. And of course, if they communicate, then there must be a reason why they communicate, and it must be because it somehow furthers their own goals, or it fits well within the activity that they're performing and serves some purpose as part of that activity. So there's a very strong focus here on the practical use of communication. So in speech act theory, typically every speech act has three parts. So there is the locution, the physical thing you're saying. This might be a string of letters, or it might be an airwave, a sound wave that's spread through a medium. So some kind of physical carrier of what you're actually transmitting. Then there is the illocution, which is the intended meaning, what you're trying to achieve by saying that, and the perlocution, which is what actually happens. Okay, so typically you distinguish between what's called a performative verb, and that's kind of a marker that helps you distinguish between different illocutionary forces, and the propositional content, which is what the speech act is about. Okay, so if the propositional context would be a statement about the world, so for example, the window is open, and the illocutionary force would be the way in which I take this proposition and modify it to describe what I'm trying to achieve. So there's a big difference between saying, please open the window, and a big difference between saying, the window is open. Right? So one might just be an assertion, and the other one might be a request, something that actually I want some action to occur that the other agent will perform. So the earliest approaches that attempted to use this sort of theory to define agent communication languages go back to the late 70s. So people coming from a very standard AI background, where they thought of rational action in terms of plans, in terms of given a goal, what sort of actions should I perform to achieve that goal based on the current situation. So I need to change the current state of the world by performing certain actions. And if I have an understanding of what different actions achieve and what their preconditions are, then I can plan for a certain goal. That's normal AI planning. And then these people thought, well, if communication serves a purpose, then it must be possible to describe it as such action that can be integrated into plans and that changes something in the world and can be utilized as a part of a plan. So the Cohen and Perot, for example, they introduced this model where you have these can preconditions and want preconditions. So can preconditions are things that have to hold for something to be possible in the world. And want preconditions are things that the agent has to intend, otherwise they would not use that action. And so they define that a speaker would request an action of a hearer if the speaker believes the hearer can perform the action, if the speaker believes the hearer actually thinks they can perform the action. But also there is a want precondition, which is that I want to issue this request, right? Otherwise there is no I'm not coerced into asking someone for something unless I want to. And the effect is a very small thing. It doesn't bring the action about. All it does is that now the hearer knows the speaker wants them to perform this action. Okay? The crucial thing here is that whether or not you actually will use these actions depends on what you're trying to achieve and your intentions. So they had to introduce these additional actions they called mediating actions, which are local mental actions. They do not depend on what the other does or on what's true in the world. And so here is an example for such a mediating action. If you, just by telling someone, please perform an action, they won't do it, they need to invoke themselves an action that would cause them to want something just because somebody else wants them to do it. Okay, so you can already see the tension here between individual autonomy and what messages are trying to convey. So by and large, the semantics that standard agent communication languages use, for example, the FIPA ACL, which is kind of the de facto standard in agent communication, they typically all rely on saying something about mental states. So I don't want to go into details of this example, but basically in this communication language, they define 22 different speech acts, and they're all derived from two definitions. One that's informing somebody else of something, and the other one that's requesting an action of someone. Okay, so you have these feasibility preconditions which say what needs to hold for this speech act to be successful, and the rational effect, which is not exactly a post-condition. It's more like what we would hope would happen if the speech act is successful. And that may depend on various conditions. For example, in the informed speech act, a rational effect is that the hearer will believe the proposition, but of course that's not under the control of a speaker. So this is often called mentalistic semantics within the agents field, because it relies very strongly on internal notions that other agents do not have access to. Now, of course, if I have designed all the agents, and if they're programmed in such a way that their beliefs, for example, change when they hear certain things, then I can verify that the desired effect has been brought about and that the speech act was used in a correct way. But in an open-ended system, that's very hard to do. So that's why people came up with other notions of semantics that are not based on internal states of agents. So there's, for example, this idea of commitment-based semantics, where, for example, if I inform you of a fact, it doesn't cause you to believe it. What happens instead is I am committing myself to believing it. Right? So there is some publicly visible, if you like, store of commitments where different agents make pledges that are publicly observable. And we cannot say anything about whether they hold certain beliefs, but they have committed themselves to a certain belief or a certain action. And typically these commitments can go through states. So for example, if I request Marco to perform an action, then there is an initial commitment that's unset because he hasn't said anything about it. Then maybe if that commitment, if that request has a condition, so if I tell him when it gets too warm here, please open the window. So then, if he says yes, I'll do that. Then it becomes pending, but of course, until it gets cold, he doesn't have to do anything. So it would only then become active. And then if he does the right action, it would become fulfilled. If not, it would become violated. And there may be certain circumstances under which he is capable to cancel it, or I'm able to cancel it. I say, you know, they've just turned the air conditioning on. Marco, you don't have to do this anymore, what I asked you to do earlier on. Okay, so this still doesn't give you any guarantee that things will happen the way you intend them to happen, but at least you can track what's going on with regard to what people have expressed and what then actually happened. So at least that's then verifiable. There are other approaches. So there is also this if we look more at protocols, then so here is this notation is called agent UML. It's a bit like normal UML, but you don't have to understand the details. Basically, it describes different roles that agents can go into and how they would talk to each other. So this is a very famous protocol called the ContractNet protocol, where the so-called initiator wants to commission a task to be done by some agent and sends out a call for proposals. Some agents will refuse. Some agents will say they didn't understand the request. Some agents will make a proposal, for example, quoting the price that they are demanding to perform it or the quality that they can deliver. Then the initiator will maybe accept some of these proposals and reject others, and once performed, the participants who have been allocated tasks will, some of them may fail at the tasks, some of them may inform the initiator that the task is complete, or point them to the result. Let's say the result is a web page or a product or something. So protocol-based semantics basically says when a portion of this has been already uttered, then the meaning of that is the, if you like, the tree or the set of possible things that can still happen, right? So if I've said yes to a request, then the semantics of that would be that if I'm capable of doing it, it'll happen. If I'm not capable of doing it, it won't. Right? So it's kind of the remaining options of what can still happen. It's a bit like viewing like communication like a script. And if I've reached a certain point, then that's where the meaning is the sum of all the things that can follow on from that. Now, there is a whole different area within the multi-agent systems field that is concerned with decision making. What I've said so far are only ways of describing either of implementing a standard way by which agents can talk, and there are many, many other formalisms. I've only given you examples, but it doesn't say anything about what decisions one should make. So given certain choices, what should I say? And by and large, that sort of work is a little bit disconnected from agent communication languages and protocols, because in order to make good predictions and solve the problem of what one should say, one has to be much more specific about the setting. It's very difficult to do that when you have a very broad communication language and ontology, and you could say just about anything. So instead, in more game theoretic or decision theoretic areas of AI, of agents and AI, people focus on very specific protocols. So for example, what I'm showing here on this slide is a type of iterative negotiation or bargaining protocol where you make proposals, the other party can accept or reject, they make a counter proposal, and so on and so forth. Now, of course, you have to be very specific about what sorts of proposals can be made after previous proposals for this terminate and to actually give a result. And then, depending on what assumptions you make on the outcomes, you can say something about what the optimal strategy would be, what an equilibrium might be in the game theoretic sense, and so on. So this is a very big area that's currently very popular and very successful, because it is very mathematically rigorous and can make very specific statements about appropriate behavior or the behavior that should be expected of rational actors. It is, however, plagued by the need to be very, very specific and focus on a very, very specific scenario to produce provable results. In particular, the results depend on a lot of conditions, on a lot of parameters. For example, once a contract is made, can it be enforced? So if I accept your proposal, will I actually participate in it? Can I transfer utility? So are we talking about just, for example, trading goods or compromising on doing different things for each other? Or do we also have money with which we can make side payments so we can compensate each other for our efforts? And then, of course, knowledge and rationality of participants. So it has been, a lot of these approaches focus on idealized conditions where every agent knows everything and is perfectly rational. Many experiments show that that's not the case when you're interacting with humans. But of course, it depends also what you want to build, whether you want to build artificial systems or systems that work with humans. Now, the grand challenge in this area, I personally believe, is understanding better what decisions are rational in a communicative setting. So, given what I'm trying to achieve, and given a specification of the things that can be said and that we can talk about, what should be the thing that I say next? This is a key problem in many areas, and the reason it's relevant to essence, I believe, is that whatever decisions you make are obviously relative to the expectations you have about their consequences. And once you've made them, those expectations are updated and actualized because you observe new consequences, and that feeds into the picture you have of the communicative space. It also situates communication in task accomplishment and in the real world. So how do I mean that? If you look at, so presume you have a robot who just gets environmental feedback in terms of, let's say, task success or its battery level or some sensor, some image of the environment and so on. And then if you provide that robot with a way to interact with other robots, there is a very big gap between, let's say, these high-level protocols that agents might use to talk to each other. Let's say he wants to get another robot to go get out the way, and the grounding in the environmental feedback that actually should determine what communicative decisions were good or bad. And this is kind of closely related to symbol grounding, but also closely related to learning, in the sense that a pre-assumed purpose of saying something has to be updated and actualized by what you actually see in the environment. Now, I want to finish. I've almost used up half an hour already, but I want to go briefly over a few things that we've done in my group that go some way towards trying to address this issue. And they come in kind of two lines of work. One is on learning, and the other one is on planning. Even though learning sounds more advanced than planning, I got interested in learning much before I understood that maybe you should look at planning before you understand learning. But that's the way things go. Sometimes you do things backwards. And so none of what I will present addresses the whole issue, but partial aspects of the problem. So calculating what options you have and what you're going to say and estimating how much they're worth, reaching agreement on your view of the world with others, tracking success and failure of past decisions, and generalizing from individual experiences. So I'll give you a few examples for these things, and I've given references to the paper, so if you want to discuss any of those further, then we can do that anytime over the next few days. So I want to start with what I did in my PhD, just because I sometimes forget because it's so long ago, and actually I think it was actually quite a nice idea. So I was interested in these things that I called interaction frames. So they're like little chunks of conversation. So I think this is kind of, this is what different frames might look like. So they're kind of subsequences or initial subsequences of what might be a longer dialogue. And what they have is they have variables in them, so they're kind of slightly generalized patterns. And then therefore, you can store your experiences with them. So these C's at the bottom, they're kind of substitutions for the variables that capture past observations. And the thetas in the middle, they're kind of conditions, facts about the world that you observed to hold when these experiences happened. So essentially you have a pattern of a part of a conversation together with the details of what was true when that interaction occurred. So what this enables you to do is basically to experience, as you interact with others, capture your experience with those interactions and try to optimize your strategy. Right? So we used reinforcement learning to find out what are the next things that could happen, how good or bad were they in the past, so which ones should I activate and which ones should I use. The interesting thing about that is, of course, because this is a conversation, for example here, if I issue the request, then somebody else actually performs the action, so I cannot anticipate. Just by activating this, it doesn't mean it will happen. It means I do the next step, and then I hope that others will do their part. So we also used this for argumentation, where I think this was kind of the most elaborate example. So if you look at the different, we looked at the different parts of a complex argumentation-based dialogue where two agents are negotiating something by exchanging arguments, and we looked at the different stages and the transitions that can occur between them. Okay, so you have initial proposals, then they can be challenged. The other side needs to provide a justification if there's a challenge. Justification can be attacked, so maybe you make a concession, and then more challenges may occur. And it was quite interesting to see that you can build these more complex conversations out of these individual building blocks and do that within a framework where the agents can learn what to do at every step. Oh, this didn't come out very well. So we generalized that with a colleague of mine, Matthias Niklas, because we realized, well, hang on a minute, rather than thinking about the individual experiences and how I should use those in the future based on what I've learned, we can just look at the global system and look at the likelihood and the conditions under which certain things are said, and capture meaning in such a way. So we call this structure expectation networks. It's essentially nothing. It's essentially a very similar idea. They're just sequences. It's just a graph of possible utterances, and the sequences of utterances we can observe, annotated with logical conditions and with the probabilities that depend on what we've expected what we've observed in the past. And so this we also call it kind of empirical semantics in a sense. So instead of making a priori assumptions about what the things the agents say mean, then we just determine the meaning by seeing what has happened in the past. Of course, you cannot bootstrap that without having an understanding of what these messages mean in the first place. So it's not the whole picture, but it's good for the adaptation part. Very recently, we came back to this sort of work with a slightly different take on it. So this is a little bit hard to read, but if you go through the things that are connected with arrows, that gives you kind of a protocol for buying something. So you request something with certain conditions, and then there are different answers the vendor can provide, and you go through this until you either conclude the negotiation or fail. And the crucial thing here is the conditions under which the different transitions occur can be annotated with with constraints. So what you can do is you can take the trace of many such conversations and use machine learning to derive what conditions were true under what situation. So for example, I ended up buying a car that was at least £20,000 worth whenever I initially asked for at least a capacity of 7 people to fit into the car, right? So you can find out these correlations from mining the context of what you've observed in terms of communication. So on the planning side, what all this learning stuff didn't do is it doesn't really tell you, it's not generative. It doesn't tell you where did the initial idea for the protocol or for saying something in a particular situation come from. So if the agents are already out there and if they're doing meaningful things, of course you can detect patterns. But the question is where does that behavior come from and why did they do it? So this is why we turned to planning a few years ago, because why planning? Because planning provides a very simple symbolic model of rational activity. So as I said before, in planning you have an initial state, you have a goal you want to get to, you have specifications of actions that tell you when you can apply these actions and what those actions change in the world, and there are plenty of algorithms that will help you synthesize sequences of actions to achieve a certain goal. So what I thought was, well, if communication is useful, it must be possible to plan it into a plan that you have. Turns out, it's not that simple. When you say things, you have many, many options. So imagine a protocol which starts with making an offer, and then sometimes it succeeds because the other person takes the offer, and sometimes it fails. It's the search space of all the things you might offer is not really determined by the goal you're trying to achieve. So for example, if you, I can actually give you an example. So if you take this very simple domain where you have a red agent and a blue agent, and they have to deliver parcels to certain locations, so the parcel is the box and the depot is the cross, and they have to take the respective parcel to the depot with the same color, then of course if I made an offer, it would be, in a rational way, it would be the selfish one, the middle one. I would simply ask the other agent to carry my parcel and their own parcel, right? So in a perfect world, I don't have to do anything. Now we know that this won't work because there is no reason for the other agent to take that offer. And, but also it's kind of not very satisfying for each of us just to do their own thing, because that's too costly. Instead, we can carry the other person's parcel if they do the same in return. So this already tells you that if you had a planning specification of this whole domain, there are many, many different possible deals. This is a trivial scale problem, but if you did this in the real world, and it's very hard a priori to make a decision about what is the thing that I should say that will actually work. So the overall problem is too hard, and therefore we focused on some sub-problems to understand the problem better. So one thing we did is use argumentation. So the first thing we thought was, well, okay, before even agreeing about what to do together, you have to agree on whether a particular course of action actually achieves the right thing. So you have to find out whether you agree about the world. And we developed this argumentation-based method to resolve conflicts about among the domain knowledge of the two agents. And this is based on introducing this notion of acceptable plans. So a plan is acceptable for two agents if it's acceptable to everyone individually. And so what would happen if there is disagreement is that I propose something, you say no, then I try to convince you that it works, and you fire certain attacks at it, and then we go through an iterative process where either I can defend my plan against your attacks, or you win. So to give you a more practical example, we built this little application where there is a robot that has partially erroneous knowledge about the world, or maybe simply, let's say it's a search and rescue situation and there is debris and they can't see everything, and then you can give them instructions. So for example, here you can see this blue path to the goal actually goes via an obstacle that the robot doesn't know anything about. So you, as the human, or as the other party who might know, could say, well, this plan won't work because there is an obstacle, and then you would have to convince them that therefore the plan will break at some point. And of course they may have reasons why they think you are wrong, and then you fight it out, and in the end, if you achieve an agreement, you have a plan that works for, that both sides think is acceptable. The other problem we looked at, and this is the final thing I'm going to talk about, is multi-objective planning. So agreeing on whether something works doesn't mean you will agree to participate in it. That depends on your own goals, and the agent's different goals may conflict, and as I showed you in this example, there are different solutions that all have different cost to every agent, and of course there is an ideal solution, which is the rightmost one, that's the most effective thing to do, but it's not necessarily the case. It's difficult to identify these plans and convince the other that they will do it. So this is a strategic problem, and in the general case, again, it's quite hard to define. Depends on many problem parameters. For example, if you can't enforce contracts, then it's almost a meaningless problem. So it's very hard to talk about this in a planning context, or if the agents are untrustworthy. But under certain conditions, we developed some algorithms that can identify finding these deals even in large-scale domains. So this is an iterative method where you have an initial proposal, and then every agent individually tries to make it better. And for certain classes of games called congestion games, you can do this pretty fast. And so here you have an example of a network routing where there's 3 agents delivering parcels to different locations, and they find a plan that is better for everyone if they follow it. So this is very much about, what is this to do with communication? This is very much to do with calculating what sorts of things you might propose, which in a planning domain that's sufficiently complex is difficult in itself. And also how you might balance, if you want to negotiate, maybe I would start with a very selfish plan, but then I want to have that dial where I make concessions slowly. And in a large world, those might be very difficult to calculate. Okay, so what I've tried to do in this talk was to give you a very quick introduction to some of the things people care about in agent communication. Firstly, general ideas about languages and protocols and semantics. And nowadays, these are seen as kind of providing the scaffolding for a lot of agent-based systems when you build them. Many people consider the issue of what languages should be used and what protocols should be used and so on as something that's been dealt with. That's not something that people do much new research on. But and instead they focus on these very specific settings where they can make much more specific predictions of what optimal behavior should look like. For example, in auctions or in voting theory, and in these very, very specific scenarios. So to me, the conclusion of that with regard to this challenge I tried to outline regarding rational decision-making in communication is very much a matter, I think, of generality. So if a setting is very specific and I know exactly my options, so we know the standard learning techniques or decision-making techniques where if you give a robot a certain state space with sufficient experience, they will learn the optimal strategy. The problem really lies in the level of generality at which a domain is defined. So if you have a knowledge-based language, a relational language that tells you what objects exist in the world, what different things you can say, and worlds where every plan to achieve something has to be computed first out of many different options, rather than being, you know, one option out of 5 given things, then this whole issue becomes very challenging. And I tried, all of the examples I've given of our own work are trying to push that envelope in the sense that we're aiming for kind of scaling these things up and coming up with heuristics that work in larger and larger domains. So that has been very much our focus. In return, we have not integrated all of this into one mega thing, but we have 3.5 years of essence left to do that, and I think there's many interesting things that we can do that lie ahead. And that's me. Thank you very much. And we have maybe a couple of minutes for questions. Nico has the microphone.
Hi, so you talked a lot about finding optimal actions, which it might, for some of the decision problems and gate problems that Essence are interested in, may be overambitious in that you'll be looking at games that lack any analytic solution. And furthermore, optimization depends on a specific definition of rational behavior, ones that humans notoriously deviate from, sometimes in very interesting and beneficial ways, actually. So I'm wondering to what extent you really mean optimal in its technical sense, and I'm wondering to what extent Essence is going to be interested in models of behavior that are coming out of behavioral economics, the kind of work of Dan Ariely and Tversky and Kahneman.
The driver behind this kind of work that I've presented is that with regard to certain knowledge and assumptions you have, you want to do the best thing. Now, the best thing is not, but you also want to, for example, if the other agent has a bias, of course you want to propose something to them that will appear appealing to them. So it's not optimal in that sense of having, you know, this world of choices and the agents together are trying to do the best thing. What it rather is that you, out of the things you can say, you want to choose your best bet. And therefore you will kind of be optimizing to certain criteria. Now, will these criteria be a strict utility and you know, or will they be other things? Will they be anchoring and framing and, you know, kind of, you know, things that people use in negotiation and that just work because people respond well to them? I don't know. But I certainly think it's going to be, in any case, all these problems are way too large to have kind of real optimality. So it's more a question of, if you like, a better word is that you want kind of a normative solution. That you want something where you can say, I used a sensible method to pick the best thing out of the options that presented themselves to me, rather than I can prove that, you know, this exact move was the best thing I could do. And of course it's a lot about reasoning about the other side. It's not so much whether, so, you know, the best thing might not be, very often will not be what works for me, but what is acceptable to the other person. So I have to account for their limitations as well. If they can't see that it's the best thing, then I'd better go with that. So, or explain.
And I'm not sure whether we're going to do that in Essence, but at least some people in Amsterdam, well, I'm at least interested in that. And I have actually a postdoc, who's not here, but who is actually going to work on that. So saying, because as I will later show, a lot of communication is not possible if you use standard models of optimal behavior. And now we will see whether if you use models that are developed in behavioral economics, whether more communication is actually possible. Whether persuasion is possible if people are less than completely rational. So you try to use more descriptive ways of how people actually behave to see whether you can explain more of actual communication. So I think maybe that's also going to be used in Essence. So yes, I do think we're going to use models of behavioral economics that are developed in behavioral economics in Essence. Yeah, I understand that, because otherwise it makes.
I also should say that I mean I have obviously only spoken about kind of things I'm interested in, right? So I don't speak for everyone. I mean I'm sure many people will disagree. So.
But I agree, we should.
This is a somewhat orthogonal issue, but I think in terms of realistic models of human interaction, although it may be the case that people have negotiations of the kind that you mentioned with your parcel case, I think what tends to happen very often is people volunteer an altruistic action, but they keep a tally. And they expect at some point reciprocity. So it's much more diffuse, more global, and there's more general social norms that come into. So it's not. I think you've atomized it in a way that is quite rather unrealistic.
Yeah, definitely. I mean, one of the big problems is kind of the estimation of the worth, and that might be something that indeed is kind of accumulated over time, or also follows other criteria. I mean, so I'm not claiming that it's the worth you estimate would necessarily be the immediate worth you will get out of it. There may be externalities or other factors that you take into account, and then you maybe optimize. But I would still claim you kind of optimize out of those choices. You would still one criterion might be, let's say, fairness. Over time, and that would maybe shift your model of how much every option is worth. But you would then still make a choice among the options you have. That simply takes that into account, and that might be certainly the more challenging thing is what you've mentioned is so I'm less worried about taking factors into account that are not just based on self-interest. I think that can be probably modeled. I'm more worried about this long-term thing. I think that's much more difficult, this abstraction of